So in the last discussion, we highlighted the spatial information representation. We differentiated between map and sketch, and then we also defined and highlighted the salient types and characteristics of maps. Then we also looked into the key elements of maps, where we put before you the significance of scale and projections. Especially in the context of real world spatial information, that is the three-dimensional feature onto two-dimensional flat plane, and the significance of map projection is very critical and complex that you understood in the previous lecture. So spatial representation in a map involves determining the geographic locations of or features over the Earth's surface. Now today, moving ahead, we look into another very important element of spatial information, that is the georeferencing. And the idea of depicting the Earth on a map, a flat map, is easy to imagine and even simple to understand, but the actual process of a map projection is really very complex task. So here we would look into some important terms and to understand some of the basic features when we are representing the Earth onto the three-dimensional Earth onto the flat plane, that is two-dimensional. We all know that the Earth is a complex three-dimensional object with physical dimensions including height, width, depth, mass, and density. An important physical characteristic is its non-straight curvilinear surface. This curvilinear property adds complexity to depict Earth to a flat surface. Due to the Earth's curvilinear surface, map projections always hold a degree of distortion, which we discussed in our previous discussion. In this unit, we will discuss about the concepts involved in transforming three-dimensional Earth into two-dimensional maps on paper or in two-dimensional flat screen of computer. So it is essential to know about the concepts of geoid, ellipsoid, datum, and coordinate system. First, we begin with geodesy. Geodesy is the science concerned with study of shape and size of the Earth. Now you need to understand that why we are emphasizing this geodesy in our discussion. Because when we are converting the three-dimensional Earth onto flat plane, these terms and this knowledge is very important when we prepare a map on flat plane. So geodesy deals with the measurement and representation of the Earth in geometrical and gravimetrical sense. In geometric sense, it deals with the study of shape and size of Earth's surface. In gravimetric sense, it deals with the study of equipotential surfaces of the Earth gravity potential. Every geodetic measurement is a function of gravity field, which may vary from point to point. The study of geodesy begins with mere curiosity and the never-ending human desire to explain the Earth's unknown through logic. The first remnant of geodetic analysis started way back, especially in the Greek period, when Homer in 8th century BC imagined Earth as a large flat disk. Thereafter, Pythagoras in 6th century BC viewed Earth as a perfect sphere. Aristotle in 4th century BC advocated for a spherical Earth, as he noted sailing ships always disappear into the horizon rather than becoming smaller dots. Newton theorized gravity and proposed that Earth's shape slightly bulged out at the equator due to the greater centrifugal force generated by rotation. The equator bulging produces slight flattening at the pole. This change, which came into the 17th century with Newton's theory, the Earth was thought to be in a spherical shape. Earth's rugged and irregular surface is difficult to represent the positions of Earth features because it's not smooth, it's very rugged. There are high uplands and there are many lowlands also in the form of depressions. To effectively represent the shape and size of the Earth is a big challenge. The closer a model comes to the actual surface of the Earth, the better it is for geographic positioning. So in that context, geoid is the term which is an approximated figure of the Earth, which is a sea level equipotential surface. The surface of the gravitational potential remains equivalent to its strength at mean sea level. Geoid is not a smooth surface. The gravitational pull is not uniform throughout the Earth's surface because of variation in density inside the Earth. This results in undulating geoid surface which is not so smooth and regular. Now in this particular diagram, we are representing the North and South America, and if you look here, now you can see the African and Indian subcontinent part. But in between, there are many oceans, great oceans. It can be Atlantic, Indian Ocean, which is visible in this particular figure. So these depressions, they offer us the irregular surface over the Earth's surface. Not only that, but we also have high mountains over the Earth's surface. So all of them, they create not so smooth surface. Instead of that, they are irregular in shape. So the spatial representation is built upon the advances in modern geodesy to depict Earth's true shape. With satellite imagery in modern day, it is established that the Earth is a nearly spherical object that bulges in the middle and flattened at the poles. In this regard, ellipsoid can best represent an Earth as it poses a near resemblance to its shape without the inherent complexities. So ellipsoid is the Earth's, it is an ellipse rotated upon its minor axis, which is known as the axis of rotation or axis of revolution. The ellipsoid's flattening causes two unequal axes, as you can see in the diagram also, a longer axis and a shorter axis. And the diagram also represents the difference between the shape of sphere and ellipsoid. So if you look into the lower diagram, the C diagram, the major and minor axis of ellipse, the north to south axis through the Earth's core is the shorter axis and is called as minor axis or polar axis. The east to west axis through the Earth's core is longer and is called as the major axis or equatorial axis. So now we are aware of the three approximations, that is geoid, sphere and ellipsoid, which are used to define Earth's true shape in different ways, which are so critical. Actually, we are trying to first understand the surface feature first, the globe first, the Earth in nature, how it is appearing, how it is visible to us, and then we are trying to replicate it into two-dimensional flat plane. So we have to take into consideration all these things, because all kinds of projection, they come with some kind of distortions which we have discussed earlier. So spatial representation and geoid, sphere and ellipsoid, I would say that the geoid is a reference from which elevations or heights can be measured. It is the reference surface for ground survey. The horizontal and vertical positions are mapped with reference to the geoid surface. So elevation are determined with reference to the geoid surface. Now assuming that the Earth is a sphere, it simplifies the calculations and works well that show a large area of the Earth, that means small scale. However, when working at large scales, an ellipsoid representation of Earth is required, where we can say that horizontal positions are adjusted to the ellipsoid surface, because the irregularities on the geoid surface make projection a far more complex The sphere is the reference surface for larger area representation, that is small scale maps of countries or continents. This is because the difference between sphere and ellipsoid is negligible while mapping large area on a small piece of paper. There is also far less complexity than the ellipsoid. At a small scale, for example 1:1 million maps, sphere proves adequate along the equator, near the equatorial plane, but fails at locations closer to the poles. With large scale, when for example 1:10,000 maps, the difference between spherical and ellipsoidal approximations are significant. So we need to take the Earth's oblateness into account, and the diagram gives you an impression as to what is the difference between sphere and ellipsoid, and in that context this discussion is very important and significant. So for spatial representation we require a reference ellipsoid, which is defined as standard ellipsoid. The reference ellipsoid, over the years numerous reference ellipsoid have been with the measurements taken at different source point on the Earth. At least more than 20 determinations of Earth's radii and flattening have been attempted from measurements taken widely at different locations for specific purposes. These reference ellipsoids are different in source data locations. Certain reference ellipsoids work better than others for certain applications and also for certain regions. So they are application specific as well as region specific. For example, Everest 1830, which is very commonly we use for Asia region, the countries lying in and around Asia. Whereas WGS 84 is more universal and most widely used reference ellipsoids. It is determined from satellite orbital data and considered more accurate. But here WGS 84 is for the entire Earth. So this is what very important in the context of reference ellipsoid. So now we have to reconcile our need to work with a simple model of the Earth's shape with the undulating Earth surface, which we are calling it as geoid. So to align the geoid with the ellipsoid or sphere representation of the Earth and to map the Earth surface features onto this ellipsoid sphere, the alignment can be local, where the ellipsoid surface is closely fit to the geoid at a particular location on the Earth surface, or geocentric, where the ellipsoid is aligned with the center of the Earth. So how we choose to align the ellipsoid to the geoid defines a datum. So datum describes the position or orientation or even scale relationship of a reference ellipsoid to Earth. A datum is a reference on the Earth's surface against which positions are measured. Datum also defines the origin of the coordinate system from where the measurements are made. And there are hundreds of locally developed reference datums around the world. A specific point on the Earth can have substantially different coordinates depending on the datum used to make the measurement. And in modern day, when we are talking about spatial information, that too in digital format, these datum are very much area specific as well as application specific. Present day datums based on increasingly accurate measurements on the Earth are intended to cover large areas. So the geodetic datums are generally classified as either a geocentric datum or a local geodetic datum. Geocentric datum is globally centered and adequately approximates the Earth's size and shape as a whole. You can see this in this diagram also. The center of the reference ellipsoid coincides with the Earth's center of mass. In the top diagram, it is very clearly being positioned and displayed. Many of the modern datums use this geocentric alignment. These include the popular world WGS 1984 or even the NAD 83, which is for North America. So geocentric datum couples a geoid with the ellipsoid at each element's center of mass, as it is being represented in this particular diagram. There are many local datums also. The choice of datum is largely driven by the location of interest. As I am saying, the choice of geographic space which is under investigation on, or that phenomena is being represented of any specific geographic area or any specific application which we want to conduct, depending on the geographic space which we want to depict in our map. A local datum couples a geoid with the ellipsoid at a location on each element's surface. So local datum is used to characterize a particular region where the reference ellipsoid and the Earth's shape coincide. You look into this diagram. It might appear as the same, but here the local datum couples a geoid with the ellipsoid at a location on each element's surface. Both these diagrams, the top one and the bottom one, they are representing the local datum. The center of the ellipsoid is often located away from the Earth's center of mass, thereby providing a poor representation of the Earth as a whole. A good example can be Europe is being represented by ED50. It is more directed towards representing smaller European countries in the continent of Europe. The classification of geodetic datums offers a degree of user control which suits the application or location best. This form of user control location specific datum dependent on individual characteristic rather than using a more general datum. So there can be two types of datum. One is horizontal datum, which provides a reference frame for coordinates on Earth. So horizontal datums empowers the users with a geographic coordinate system for determining accurate point position. Whereas another kind of datum can be the vertical datum, which provides a contiguous, consistent reference from which the topographical elevation and bathymetric depth are measured. The vertical datum is used to define the positional height as it relates to a determined reference. So height measurements reference to the sea level in terms of datums, where the average sea level, which is called as mean sea level, is taken into consideration. But this sea level also have different possibilities. There can be high tide sea level or low tide sea level, and in between we take the mean sea level. So the relationship between sea level and height measurement is also depicted in the diagram which is being represented in this particular slide. So elevation is significant along with Earth's shape. It has relevance in locating any location on Earth. Elevations defined with reference to a sphere, ellipsoid, geoid, or local sea level. This influences the location of latitude and longitude. So in this slide, we are representing the geodetic datums where the topographic surface has undulations over the Earth's surface. Not only that, there is also sea level differences also. So all of them, they make the spatial representation in two-dimensional form a far more complex entity. Just to summarize the understanding for geoid, ellipsoid and datum, these figures give you a fair idea. It is a simple model of Earth's shape with the undulating Earth's surface can be called as geoid. The solution is to align the geoid with the ellipsoid or sphere representation of the Earth and to map the Earth's surface features onto this ellipsoid. The alignment can be local where the ellipsoid surface is closely fit to the geoid at a particular location on the Earth's surface, or geocentric, where the ellipsoid is aligned with the center of the Earth. Now, how we choose to align ellipsoid to the geoid defines a datum.